Welcome to Lecture 2. We are going to continue our discussion from last time, in which we introduced a whole lot of terminology and tools in order to start discussing one and two-dimensional motion. So one of the distinctions that we made in Lecture 1 was the difference between displacement and distance. Distance, on one hand, is a scalar quantity which only has magnitude, and it considers the entire path that's taken. Whereas displacement is a vector quantity, and it has to do with the difference between the initial and final positions. Okay, and so it has both magnitude and direction to it, and the path does not matter. It just matters where you are compared to where you were. Okay, after getting that out of the way, we discussed velocity versus speed, and we said that although these are very similar quantities, velocity is a vector which has both magnitude and direction, and speed is a scalar. So similar to this discussion of distance and displacement, where one was a vector quantity and one was a scalar quantity, velocity and speed likewise are vector and scalar respectively, where speed, the scalar quantity, is effectively the magnitude of the velocity. And symbolically, we define these quantities as being the time derivative of your displacement vector. Okay, and then we also introduced the idea of thinking about these quantities in terms of a plot, for example, a position versus time plot. And I think it's probably better to talk about this as position rather than displacement. It sort of makes a little bit more sense the way it's plotted. And so the slope of this position versus time graph is going to be what your velocity is, because it is a time rate of change, which is some sort of slope. So on average, that means that your average velocity is going to be your change of position divided by your change of time. So for example, if we have a curved path, then we take a tangent line like what you're seeing here at point P and Q. Okay, and then it would be this delta xp divided by delta t. In other words, rise over run will tell me the slope at this point P, and that will be my velocity. Okay, finally we introduced acceleration, which is the time rate of change of the velocity vector. And because it can involve any change of velocity, that means that if the speed changes or the direction changes or both, then that's some kind of acceleration. So for example, most people don't tend to think about it, but if you are traveling around in a circle at a constant speed, you are still indeed accelerating because you're constantly changing directions. At one point in time, your your velocity vector is pointing like this, and at another point in time later, your velocity vector is pointing like this, right? These things might be the same length because your speed is the same, but your direction is changing all the time, and therefore there's some sort of acceleration. In this particular example, we would call that centripetal acceleration. Okay, so putting this together with what we discussed regarding the velocity, the position versus time graph, we can also write a velocity versus time graph. And if there is a constant acceleration rate for velocity versus time graph, then you will have some sort of a straight line, like so, on the velocity versus time graph. And on the position versus time graph, if there is a constant non-zero acceleration, you'll have some curvature to this graph. And last time we left off with posing the question as to why this exhibits this quadratic shape to it rather than a straight line. So maybe you've come up with the answer to that. I'm going to hold you off for just a few more slides and we will demonstrate why that's the case when we derive our equations of motions. But in the meantime, why don't we apply some of what we are thinking about in terms of graphs to a specific example. So let's say, for example, that you are standing right here at the origin. This is you. And Sally moves to your left. For 2 seconds, she walks to your left. And we want to represent her motion through a position versus time graph. After she walks that 2 meters in 2 seconds, then she stands still for another 3 seconds. So what does that look like on a position versus time graph? Here are some possibilities. If you want to pause the video, see if you can ascertain what the correct answer is. This is an example of what we would call a clicker question. So if this was an in-person class rather than an online class, I would give you a chance to discuss this question or questions like this with your neighbor, and then you would respond on a remote control that we call a clicker. And then we would discuss what the answer is. So in lieu of that, if you want to just pause the video and think about it and see what you think the correct answer is, then unpause it and then I will go over the answer. Okay, so if you've thought about it, hopefully you have been able to deduce that B is the correct answer here. Why? Well, if she's moving to your left and you are at the origin here, she's moving into the negative x direction. So she's starting at the origin just like you, and her position is changing into negative values as you see here. And then once she goes 2 meters, that should be right about here for 2 seconds, right? So 2 meters and 2 seconds. That's where she begins to stand still for another 3 seconds. Okay, so B most accurately depicts this kind of motion. All right, so now let's do another example where we are thinking about a similar situation, but instead of graphing something whose motion is described to us, we're going to look at a graph and try to understand something about the motion. So if you were presented with this particular position versus time graph, you might be asked, for example, where the object has the greatest speed. Okay, so go ahead and pause if you would like, and I'll go over the answer. And so if you take a look at the graph and you're trying to figure out what the area is that has the greatest speed, you have to bear in mind that this says speed. It does not say velocity. So we don't care whether we get a negative answer or a positive answer here. We just care about the magnitude. Okay, now remember that velocity is the slope of this position versus time graph. So when the slope is equal to 0, we can already rule out any of those possibilities because that's basically where you're standing still. There's no speed going on there. Okay, so we can rule out, for example, 3 seconds because that's taking place where there's a slope of 0, and we can rule out 7 seconds for the same reason. Okay, so now it boils down to a question of, well, it could be when I'm heading up with this positive slope or heading down with this negative slope. Okay, now as I said, the sign doesn't matter. We just care about the speed. So it's the amount of how fast you're going, not the direction, that matters for this. And so if you think about the slope, the question is then, well, which one has the steepest slope? And you can probably tell just by eye, or you can calculate, if you would like to, the rise over the run, and you'd be able to see then that this period of time with the negative slope is a steeper slope than the beginning period of time that has a shallower slope. And so that allows us to conclude that the time period where it is the greatest speed out of these choices is time equal to 5 seconds. Okay, so let's let's take that position versus time graph for this particular example, and let's go a step further with it. So given this same position versus time graph that you saw on the previous slide, we're now going to ask the question, how would we depict that motion in a velocity versus time graph? Okay, so go ahead and pause if you would like, think about it, see if you can figure out the correct answer. Okay, and if you've come back now, hopefully you were able to deduce that B is the correct answer here. So how do I know that it's B? Well, let's think about what's going on. Remember that if there is a constant speed or a constant velocity, then that's just going to appear as a straight line. It's only going to appear as some sort of angle up or angle down in a velocity versus time graph if there's acceleration. And we know that there cannot be acceleration because then I wouldn't have these straight lines here. I would have some quadratic, some curve that we saw when there was constant acceleration earlier. So that means that I have a constant velocity with no acceleration. In other words, my velocity stays at some steady number until it changes again. So in choice B, you can see that the velocity is equal to less than 1 meter per second right here, which sort of jives with what we think the slope might be. And then here where I'm standing still, my position is not changing, my velocity drops down to 0. Okay, so that checks out. And then starting at 4 seconds, I get a negative slope and it's steeper, right? So I'm going at a faster speed for these couple seconds, and then I'm coming to a rest again at velocity equal to 0. Okay, so the upshot is that this position versus time graph and this velocity versus time graph depict the same motion. You have to pay attention then to what's written on the vertical axis before you jump to conclusions about what the motion is actually doing. Make sure that you understand how the position versus time graph and velocity versus time graph differ from one another. And we could even create an acceleration versus time graph. If I plotted the acceleration as a function of time of this motion, what would it look like? Well, there's no acceleration, we decided, throughout the entire motion. So my acceleration would just be a straight line, like so. Okay? All right, so now the time comes, we're going to get back to that question of why it is that when I do have acceleration, I get that quadratic shape to my position versus time graph. So in order to do this, I'm going to derive in the process the equations of motion using some geometrical arguments, and as my tool, I'm going to analyze a velocity versus time graph. So let's take a generic example where we think about the motion of some object that has some constant acceleration to it that is not equal to 0, some non-zero constant acceleration. Okay, so we might want to plot that motion using, for example, a graph like so. Maybe it has some initial non-zero velocity and then it's accelerating to some faster velocity as time goes on in a constant way. This is the kind of line we see in a velocity versus time graph when there's constant non-zero acceleration. Okay, now if you recall back from your algebra days, you know this line y equals mx plus b is the equation of a line. So we have basically a line here. So what is the slope of my line? Well, I already know that the slope in this case should be my acceleration rate. What is corresponding to x? Well, it's whatever's on the horizontal axis, in this case time. What is y equal to? Well, that corresponds to my y-axis or my vertical axis, so this is v. And the intercept b is going to be my initial velocity. So I can basically just, thinking about the equation for a line, come up with one of my equations of motion just by thinking about what corresponds to what. Instead of y, I've got v. Instead of m, I have a. Instead of x, I have t. And instead of b, I have v naught. But it's really the same thing. Now, to come up with the next equation of motion, I've got to think about the geometry of the situation a little bit more. What do I mean by that? Well, the area of underneath the curve, or the area underneath this line, if you will, is going to be the displacement that I've done. Okay, so knowing that, I basically just need to know what the area of a trapezoid is in order to figure out what my displacement is. So we can start off by remembering that the area for a triangle, I'm sorry that that's appearing a little bit strange for us here. Let me see if I can adjust that just slightly. There we go. And so the area for a triangle in general, you may already remember as being 1/2 of the base times the height. So the base in this case is going to be this time, right, across the bottom here. So I'm talking about this triangle here. Okay, the area of it is going to be 1/2 of the base, which is your time that has passed from 0 till time t. And then your height is going to be your final minus your initial, v minus v naught. Okay, so 1/2 of this times this should give me the area of the triangle. So now I just need to add to that the area of this rectangle below. And I know that the area of a rectangle is length times width. So the length is the same as what we had for the base of the triangle, so time, t minus 0. And the height is from 0 all the way up to the initial velocity, so v naught minus 0v, v naught. Okay, so if I add these two things together, then I should get the entire area of this trapezoid, which is to say that my displacement, the area of this trapezoid, is going to be this plus this. Okay? And I can do some algebraic rearrangement here in order to simplify this expression. So I'm going to first distribute this 1/2 into here and here, and then I can combine my like terms. That will give me a negative 1/2 v naught plus a positive 1/2 v naught, gives me a positive 1/2 v naught here and a positive 1/2 v here. Make sure you're paying attention to the subscripts here because these are not the same velocities. But remember that I also have an equation right here for v. And I can substitute this equation right in there for that v. Okay? When I do that and I do some more term rearrangement, I will see that I don't just have 1/2 v naught, I've got another 1/2 v naught, which gives me a total of 1 v naught. And when I distribute the half in here and the t in there, I come up with the following expression in the end for the displacement. And so this is my kinematic equation for position as a function of time. Okay, so why do we need all of these things? Well, they're going to help us describe and understand and solve for problems in which an object is moving in 1 or 2 dimensions. So in order to do that, let's put it all down in one place, and let's remember that we can think about this in either 1 dimension or 2 dimensions, or if we were going on to more dimensions, we could think about 3 dimensions, but we're going to keep it to 1 and 2. So here are the general equations that I just derived for you using the equation of a line and some geometric arguments of the area of the trapezoid. And now hidden within these equations are equations for 2 different dimensions, vertical and horizontal. And as I said, we could go on to a 3rd dimension, but we're just going to look at 2 dimensions. So what I'm saying to you then is that we can think about this general equation as it applies only to the x direction. To disambiguate that, it's good to include a subscript, like you see here. We could think about the same thing in the y direction. Okay? Likewise, this r is sort of a general position, but I could think about it as it applies to just the horizontal motion. Now, by the way, this horizontal component to your velocity, and this goes for this equation and this equation, it's going to be able to be figured out based on the idea of resolving a vector into its components. V naught times cosine theta will give you the x component of that velocity. Likewise, I could think about it in the y direction, and then I would have to resolve my velocity into a y component, v naught sine theta. Okay? And if these ideas here of resolving vectors are still not comfortable for you, I would encourage you to review the first lecture and also the material in Chapter 1 in Halliday and Resnick. Okay, so what we have so far are basically everything below the dotted line is what we tend to use in 1- and 2-dimensional motion. We've got an equation that describes the velocity in the horizontal direction as a function of time, and an equation that describes the velocity in the vertical direction as a function of time, and the position as it changes as a function of time, both in the x and the y directions. But what if we don't know anything about time? Sometimes you want to describe the motion of something or solve a problem in which there is motion, but you do not understand much about the time. Thankfully, and I won't derive this for you, I won't take the time to do that, but it is in your book, there's a way to look at the motion without using time. We can combine some of these equations and we can come up with a time-independent version of some of these equations. So what that boils down to is the equation that you see here. If I break this down into x and y directions, you see that it turns out as so. So you have the velocity squared equal to the initial velocity squared plus this term here, which is twice the acceleration times the change of position. And you can do that both in the x direction and the y direction. Okay. Now I'm going to preemptively ask you to think about what happens to these now 6 kinematics equations if there is no acceleration. Okay, so going back, for example, to these equations, what happens if there's no acceleration? Okay, they simplify, right? And we get back some of the equations that we may have seen before. Okay, but before we get into that case where we don't have acceleration, or maybe we only have acceleration in one direction, I want us to consider using these equations of motion for a couple example problems. So let's go over the ideal way to kind of solve your physics problems, and I want you to think about this as a process that you should probably follow, something like this, and follow a systematic procedure when you're answering these physics questions. So typically that procedure involves drawing some sort of figure, some sort of coordinate system, something like that. And you might want to define your coordinate system in such a way that you put the x equal to 0 where it's convenient, or you put the positive direction as it's convenient, and we'll see how those different choices play out as we go through some more examples. And then it's good to try and list what it is that you know and what you don't know. And within that, you know, there may be a lot you don't know, but maybe you don't actually care about some of those things that you don't know. So you might want to, while you're listing what you know and don't know, list which thing you're trying to find. What is the target quantity that you want? After you've done that, you want to think on the problem, think what was given to you, and think about what concepts might apply to this situation. Along with those concepts, once you've identified the concepts, then you can come up with what the equations are that will help you put those concepts into practice in order to solve the problem. Okay? And then you'll go through the motions of using the equations to solve the problem. And finally, in the last step, you want to check your answer to make sure it's sensible. And that's an important step that's often forgotten about, but make sure that your answer makes sense, basically. Okay, So I've already posed an example question here about a car that is at rest and then it speeds up with a constant acceleration rate. After a certain amount of time, it passes a certain position, and what we are interested in is what was the acceleration rate. We're assuming that it was fairly constant and that we can find what the acceleration rate was. So the first step in solving this kind of a problem is to draw a picture. And that picture doesn't have to be anything elaborate. You don't have to go to great pains to sketch something like what you see here. Okay, it can be any sort of cartoon. Nobody's judging you on your artistic ability, but sometimes it helps to just sketch out what's going on. It could be something as simple as just a dot representing your car. Once you have that picture, you want to define your coordinate system around what's convenient for you. So in this case, if the car is starting at rest at a certain position, I may as well make that position, that initial position, 0. I mean, I could choose to make it 10, but why would I make my life more complicated? It's better to make it 0 at time equal to 0, and then later, that 5 seconds later, then I know that its position is going to be 25, and I don't have to add 10 to whatever the 25 mark is. Okay, so here's a rough sketch of time equal to 0 and time equal to 5 seconds and where the car is in each instant. Okay, so I've done steps 1 and 2 in my procedure. The next step is to list what I know and what I don't know. So I have to think about some possible things I might need to know and what of them I already know and what I don't know. Okay, I know the position, the initial position is x equal to 0. In fact, I cooked it up that way so that it would start at the origin. I also know that the final position is 25 meters because it's gone 25 meters in that amount of time. I also know that it started at rest. By the way, this is a very common phrase in physics problems, at rest. That is for you to infer that it means velocity equal to 0. I also know that 5 seconds of time have passed by the time it gets to this 25 meter mark, but what I don't know is I do not know the car's final velocity, nor do I know its acceleration rate. In fact, the acceleration rate is the thing that I wish to find, so this is my target variable. Okay, so I've done steps 1, 2, and 3. Now I want to move on to step 4. Step 4 is where I need to identify which concepts might apply to this situation and then pick out the equations that go with those concepts. So the concepts that are applying here, well, it looks to me like I've got a car moving along and they're not telling me anything about a vertical change, so I'm assuming that we're dealing with one-dimensional motion here. Okay. Also, I said at the beginning that we can assume a constant acceleration rate. Otherwise, it would be pretty complicated for me to solve for the acceleration if it wasn't staying constant. Okay, so those seem to be the concepts here that apply. Since there was nothing mentioned about vertical motion or hills, I can rule out two-dimensional motion. And if it's asking me about acceleration, then I know the velocity cannot be constant. Okay, so once I've boiled it down to those concepts, I need to ask myself, among my equations of motion for 1 and 2-dimensional motion, which equations might be appropriate for this problem? Okay, so given that I want to know acceleration, but I don't know the final velocity, it's not very useful for me to use A, right? Because now I have two unknowns in A. I don't know velocity and I don't know acceleration. Okay. B, on the other hand, might be able to help me because I know my change of position, right? I know my initial velocity and I know my time that's passed. The only thing I don't know is the acceleration rate. Another way to think about that, I could say that my change of position is r. There's nothing stopping me from doing that and treating it more generally. Okay. C is not going to work for me either for the same reason that A won't work, and that is because I don't know my final velocity and I don't know my acceleration rate, so there's two unknowns here. That's not going to help me solve my problem. All right, so I'm going to utilize equation B next in figuring out what the answer is, which is what was the acceleration rate. So I start off with this equation. Okay, it's always best if you can to do the algebra first and then plug in the numbers. I know that when I was in introductory physics, that was not necessarily my preference, so I get it. I understand if that's not your preference either, but trust me on this, it is usually, if you can get over that initial hump of feeling comfortable with the variables, it actually does save you a lot of hassle and prevent you a lot of unnecessary mistakes. So let's take a look at what we need to do here. Well, the initial velocity was equal to 0, so I can actually just eliminate that term. That'll make the algebra a little bit easier for me. And so I've got x minus x naught, and I'm going to multiply both sides of the equation by 2 in order to isolate this acceleration rate. And then I'm going to divide by the time squared, and that should equal my acceleration rate. And if I plug in 2 times the change of position, which was 25 meters, and divide by the time squared, which the time was 5, so now I've got 25 seconds squared, 5 times 5 being 25. The 25's cancel, right? And that tells me that my acceleration rate of 2 meters per second squared is what the answer is. Okay, so I'm not done though. I've done steps 1, 2, 3, and 4. Now I want to make sure I do step 5, that crucial step of asking myself, does this answer make sense? So is an acceleration rate of 2 meters per second squared sensible? So this is like going from 0 to 60 miles per hour in about 13 seconds. That seems to be a reasonable rate for a car. Another way to think about it is the acceleration rate due to gravity is 9.8 meters per second squared, which is a lot larger number than this. So it's not something so unreasonably fast in terms of the acceleration rate that it wouldn't be feasible. Okay, so it seems to check out, and I can be confident that, yes, indeed, my answer should be 2 meters per second squared. Okay, so the next example is really just going to build on what happens next in this car's motion. So after the 5 seconds has passed, now the driver releases the gas and starts to apply the brakes. After an additional 15 meters, she comes to a stop. Just as at rest means velocity equal to 0, stop is also going to mean velocity equal to 0. And now we wish to know what the acceleration was during the braking. Okay, so we're going to follow the same steps as before. First, we're going to draw a picture, and second, we'll define our coordinate system, and we'll do it basically the same as we did before. We'll just use the same coordinate system. Remember that the car started here, went to the 25 meter mark in 5 seconds. Now it has released the gas, and the brakes are going to be applied. So it's going to continue forward until it comes to a rest at 40 meters. How do I know 40 meters? Well, 25 plus 15 that was given to me gives me my 40 meters. Okay, step 3 is to think about what we know and what we don't know. Here are some possibilities here. Which of these do we know and which we don't know? Well, we know in this case that the initial x position was 25 meters. We know that later on it's 40 meters. We know that the initial velocity is 10 meters per second. Wait, how do we know that? Where did that come from? Let's get back to that in a second. We know that the final velocity is 0 meters per second because it tells me that she stops in the end. What we don't know is the acceleration rate and the time. Last time we didn't know the acceleration rate and the final velocity. This time we don't know the acceleration rate and we don't know the time. So we might need a different equation this time. But back to this question of how do we know where this initial velocity came from? Well, if this is a continuation of the same car's motion, then the final velocity from the previous part is going to equal the initial velocity here. Right? So maybe actually I should do that in a different color. The final velocity from the previous part will equal the initial velocity here. And that means that from the previous part, that would be the acceleration rate that we had during that motion times time, based on that kinematic equation. So if I plug in my 2 meters per second squared for the acceleration rate times the time of 5 seconds for which it was moving initially, then I find that my initial velocity is 2 times 5, which is 10 meters per second. Okay, so this checks out, just based on what we learned from the previous part. So sometimes a quote-unquote given value isn't exactly given. You have to construct it from something else you know. Okay, maybe it's just a context clue like stops meaning 0, or maybe it's something from a previous part that you'd already solved for. Okay, nevertheless, we still have two unknowns here, acceleration rate and time. We wish to solve for we wish to solve for acceleration rate. Acceleration is our target quantity. So in order to get to this, let's think about what concepts apply, as step 4 guides us to do. It's really the same idea as before. We're dealing with one-dimensional motion and constant acceleration. We're not climbing hills, and our velocity definitely is changing if we are applying the brakes. Okay, so based on those concepts, what equations do we think might help us here? Also, we need to look at what we know and don't know to help us deduce this. We wish to find the acceleration rate, but we don't know anything about time. So this is not going to work for us. It's two unknowns. This is not going to work for us. It's two unknowns. Same thing here. There's really only one choice out of these options here, and that is to use the time-independent kinematic equation. In this equation, we know the final velocity, the initial velocity, we know the change of position, so all that's left to solve for is the acceleration rate, which we can now solve for. Again, solving for the equation numerically first, with variables first before we plug in the numbers, we can start by taking this to 0 because my final velocity is equal to 0, and then bringing this v naught x squared to the left-hand side equal to 2ax x minus x naught. Okay, then to isolate the acceleration, I'm going to divide off the 2x minus x naught. Okay, and that should give me my acceleration rate. If I plug in the values from above, we've got 100 meters squared per second squared, because this is 10 squared, right? And then we're dividing by 2 times the change of position, which was 15 meters. So we're going to have 30 here in the denominator. And so negative 100 divided by 30 is going to give me negative 3.33 meters per second squared. Okay, which means we have an acceleration rate which is negative. This is reasonable because the car is slowing down and it was moving in the positive x direction first, so the acceleration rate has to point in the negative x direction. Please note that if the car was moving to the left in the negative x direction to start with, and then it was slowing down, we would not want the acceleration vector to point in the positive x direction in order to slow it down. So I don't mean to imply that negative acceleration is equivalent to slowing down. But if you are moving in the positive direction, then negative acceleration does slow you down. So this is sensible. Okay, and so we should just finally ask ourselves if the number makes sense. So we are going from 60 miles per hour to 0 in about 8 seconds. Again, this is a reasonable acceleration rate, nothing too crazy. All right, so now that I've taken you through a couple examples, I would encourage you to take a look at this YouTube video that goes through some horizontal motion with and without acceleration, just for some extra practice. Moving on, I want to discuss the idea of free fall, because free fall is a very important case of constant acceleration. But take note that that constant acceleration is only in one dimension. However, the motion itself could take place in 2 dimensions. In other words, free fall is when I either drop an object or I throw an object. However, there's only acceleration in one direction because we are dealing with a case in which the only thing acting, the only acceleration rate, only acceleration on the object is from gravity. Okay? And gravity has a known acceleration rate near the surface of the Earth of this 9.8 meters per second squared, no matter what the mass of the object is. Okay, so I asked you earlier in the video to think about what would happen if we did not have acceleration in one or both of the dimensions. So in this case, which dimension do we not have acceleration rate in? Well, generally I don't find myself falling sideways horizontally, right? There's no acceleration if the only acceleration that is present is due to the acceleration of Earth, g, that's always going to act down. It's never going to act horizontally. And so I can get rid of this term from my kinematics equations, both in the velocity equation and in the position equation. There is no acceleration rate in the horizontal direction when you're dealing with the special case of free fall. Obviously, if you're talking about a car moving horizontally, then it can provide its own acceleration, and we can't just eliminate those terms. We had to consider them in the previous examples when we were trying to figure out the acceleration rate while the car was speeding up and slowing down. But when we're talking about free fall, the only acceleration present is that due to gravity. And so gravity being only a vertical acceleration means that there's no horizontal acceleration. And we can do the same thing in this equation, the time-independent equation as well. Notice that this leads to a rather boring result for us in terms of the velocity for the x direction. But this boring result is actually really, really deceptive because we don't always think about what it means. What this means is that if I take the square root of both sides here, the velocity, the final velocity in the x direction equals the initial velocity in the x direction. So it doesn't matter how the object accelerates in the vertical direction. That's not going to change its vertical velocity. That may seem obvious right now, but I'm telling you, sometimes it becomes less obvious when we consider projectiles shot at different angles. Okay, so just be mindful of that. And so if I summarize all of these kinematics equations together, once I've eliminated all of the horizontal velocity and I make a crucial replacement, I get these equations for the special case of free fall. I get that the velocity final in the x direction equals its initial velocity. And for the vertical velocity, I am going to replace this acceleration. Remember that this was plus at. I'm going to replace that with minus gt. Why minus? Well, gravity acts down, not up, in the negative y direction. I'm assuming here that I'm making up be the positive y direction. Okay? And when I make that assumption, then I plug in a minus g, because g itself is always defined as being positive 9.8 meters per second squared. Don't plug another negative into this. That's a common mistake I see people make. You don't want to undo what you've done. You've already accounted for the negative right here. Okay, so don't plug in another negative. G itself is positive 9.8 meters per second squared. Okay, and then I'm going to do the same thing for my position equation in the y direction. I will replace this plus 1 half at squared with minus 1 half gt squared. I've gotten rid of the acceleration term for the horizontal direction in the position equation for the horizontal direction, and in the time independent equation I've replaced the plus 2a with a minus 2g. Okay, and so I can use all of these equations anytime I'm solving a problem which involves free fall. So let's do an example where we do look at free fall motion. I'm going to do something simple to start with. I'm just going to drop a ball from a certain height, and I want to know how fast it's going when it hits the ground. First step, draw a picture. Again, you don't need something fancy like this. A sketch will do. And then the second step is to define my coordinate system. Now you could put the 0 at the bottom, or you could put the 0 at the top, but you've got to be careful what you mean. Generally, we want positive y to point up, and so we're going to start the ball off at 1.5 meters, and then it's going to fall to 0. Okay? Now we're going to try and figure out what we know and what we don't know. Here are some possibilities. Okay? What we do know is that the ball starts off at an initial y position equal to 1.5 meters and it falls to 0. That's what we said in the previous slide. And when you are letting go of the ball, if you see the word drop, that's another code word for you, like at rest. Drop means you are not throwing it down or throwing it up, you're just releasing it. So it's starting from initial velocity equal to 0. It's at rest to start with. What we don't know is its final velocity. In fact, that is our target variable. That is what we're trying to solve for. We do know that its acceleration rate is minus g because it's on Earth, it's near the surface of the Earth, and that's the known acceleration rate for free fall. We also don't know time. Okay, and so what are the concepts might apply here? Well, we are dealing with one-dimensional motion if we're just dropping it. I didn't throw it in an arc or horizontally. It's just being dropped vertically. So that can rule out two-dimensional motion. There is constant acceleration present, namely the acceleration due to gravity, which means there's not constant velocity. It is accelerating. And we can add this concept of free fall to the mix here too. So given all that, and given what we know and what we don't know, which of the following which of the following equations might work for us? Well, this equation here is not appropriate for free fall at all, unless you want to plug in a 0, for the acceleration rate. But there's no horizontal motion anyhow, so there's no real use for that equation. Okay. Likewise, with choice A, there's no acceleration in the horizontal direction. There's really no motion in the horizontal direction, so that's not appropriate either. Okay. Personally, since I don't know anything about the final velocity or the time, I really would prefer to use choice E here, which is the time independent equation. But it's worth saying that you could instead use C to solve for one of these two unknowns and then use D, right? So in other words, I could use C to solve for the time, right? Solve for the time, and then plug that time into D in order to solve for the final velocity. Okay? By themselves, they're not getting at what you want because this one doesn't tell me what the final velocity is. It doesn't even appear here. And this one I can't use unless I already know the time. But I can get to the time if I use C. So there's almost always more than one way to solve these problems. So the way that I'm doing it may not be necessarily the way you do it, and that's okay. The more you do these kind of problems, the more you'll find the most efficient way to solve them. Okay? Oh, and it's worth mentioning too that sometimes students find more efficient ways than me. I'm not definitely not always doing it the most efficient way. So, but the point is you can do it more than one way. We're going to choose this way that's time independent. Okay, and remember we've already accounted for the negative sign here, so we're plugging in a positive 9.8. This is minus g is negative 9.8. Positive g would be positive 9.8. We've already accounted for the minus sign once. We don't need to do it again. Okay, so in order to solve this problem then, remember that the initial velocity was equal to 0. We can eliminate that term. Okay, and then we can say that the Vy, the final velocity, is going to be the square root of negative 2 y minus y naught. And you might be worried here, well, how are we going to get rid of this minus sign underneath the square root? Well, remember that final y position is 0 and initial was 1.5. So when we do 0 minus 1.5, we'll get another minus sign in here, and this will cancel into a positive sign. And so when we do all of that, we will get square root of, and we multiply by the g, I'm sorry, I should have thrown that in there, we will get 29.4 meters squared per second squared underneath the square root. Now, if you ask a mathematical purist, you would know that when I take a square root, there's a positive or negative that's possible here, right? Okay. And so which one are we going to accept? This turns out to be plus or minus 5.4 meters per second. Okay, I need to think about this because velocity has a directionality to it and not just a magnitude. Since the ball was falling down, that corresponded to my negative y direction, and so we are going to accept the negative answer. Minus 5.4 meters per second is the final velocity of this dropped object. Okay, and so finally, the last step is to check and make sure this answer makes sense. If we claim that it's minus 5.4 meters per second, is that sensible? That's like going about the speed you might go on a bicycle, 12 miles per hour. That's not unreasonable, I think. It's not too outlandish. It sort of makes sense. So it checks off in that respect as well. Okay, so the last thing I will leave you with in this lecture is kind of a fun thing. I would take a look at this YouTube video in any of the YouTube videos that you like by this person. She's called Physics Girl, and she's awesome. She does a lot of cool experiments. One of the things you're going to be doing in your recitation work is designing your own experiments, and so getting some ideas from her is going to be really fun, and she does them in a really fun way. What you'll see in this particular video is what happens to a lit flame when it undergoes free fall. Okay, and I will see you again for lecture 3.